In this video, we will be looking at a comparison between the different traveling salesman problems that we've considered, or algorithms, the techniques for TSPs. And those are brute force, which is just to list all possible routes, and it does find the best answer. The issue is if it's a very large problem, then it becomes very, very challenging to either do that by hand or even for a computer if the number of vertices is quite large. The techniques that we're really going to focus on in this video are the nearest neighbor algorithm, NNA, where we pick a starting spot and then go to the next nearest or cheapest edge each time. The repeated nearest neighbor, where we do the NNA process, but from each vertex in the graph, and then we choose the best of those. And then the technique we did in the last video, which is the sorted edges technique. We don't worry about a starting spot. We just really grab the cheapest edge each time so that we create a circuit. And the only issues that were there were when we were trying to avoid a vertex of degree 3 and not to close the circuit before we get done. So let's take a look at one problem that uses all of these methods at once. In this problem, we have a traveling salesman problem where they're visiting 6 cities. Now, my suggestion is, and you can make your own graph that you see to the right here, or you can grab one from Google Images. I just typed in graph with 6 vertices, complete graph, so it connects every vertex. Now, we don't want to go down all of these edges. Remember, we just want to visit all 6 the cheapest way. So what I would do is start with a graph and then realize that these cities can be labels on the graph. It doesn't have to be geographically correct, just so that they're Atlanta, Columbus, Kansas City. I'm going to label this Minneapolis, Pierre over here, and then lastly, Tulsa. And you'll see why the graph is handy in just a second. Now, notice in the table that there's this diagonal with these stars, that everything above that diagonal is the same as what's below. Taking a look at the numbers that have been outlined in the triangle, the smallest value is 248, and the largest value looks to be 1071. But in this method, we're going to use nearest neighbor algorithm. So we need to pick a starting spot. So I'm going to pretend for a moment that our traveling salesman starts in Atlanta. And so I would be looking at the Atlanta line. Now, in that line, the cheapest edge is what I would look for with the nearest neighbor algorithm. And the smallest one of those numbers is 533, connecting Atlanta to Columbus. I'm also going to highlight that on my graph as I go along. And now I know that I'm in Columbus. So now I will look at the Columbus line. Right? If in Columbus, the cheapest edge is also Atlanta, the 533, but I've already been there, so it has to be a new edge. So of the existing edges that are left, I choose 656, connecting to Kansas City. Right now, I'm just going around the perimeter of my graph. Now I'm in Kansas City, so I'm looking at this third line. I've already been to Atlanta and Columbus, so of the ones that remain, the cheapest one is Tulsa at 248. So I'm going to connect Kansas City to Tulsa, going through the middle of my graph here. Now I'm at the Tulsa line, which is the bottom line in my table. Now remember, I don't want to revisit a city until I've completed all of them. So I don't want to go to Atlanta. I don't want to go to Columbus. I don't want to go to Kansas City. It's between Minneapolis or Pierre. And of those two, the cheapest is Minneapolis. So I'll travel there next. Now I've traveled to every city but one, so I really have no choice. But I'm on the Minnesota line, but I have no choice but really to travel to Pierre. So I'm going to connect Minnesota to Pierre, and I'll also find that on the table at 394. Now that the TSP is complete for all cities, we just go back home. Remember, this is a circuit, so we have to go from Pierre all the way back to Atlanta. And on the table, right on the line of Pierre to Atlanta is 1,361. So my total weight would be the combined weights of all of the edge connections that I've made, all 6 of those. And let's take a look at the weight. If you want to grab your calculator, you can try that as well. Okay, I have 3,887 miles using NNA. Now, in this video, I'm not going to do all of the next method. I'm going to ask you to participate in part of it. But the next method we would look at would be RNNA. And that would just be to do the nearest neighbor algorithm, but from each of the vertices. And we've already started at Atlanta. So next you might consider what would happen if I started in Columbus, So that would be what would happen if I started in Kansas City? What would happen if I started in Minneapolis, Pierre, or Tulsa? Now, I will do one of those. So I'm going to consider what would happen if I started in Columbus. So again, I'm going to use the same strategy. And the only difference with our NNA is that I really have to repeat the NNA 6 times because there are 6 vertices. So now I'm looking at the line of Columbus. And what is the cheapest edge? It actually is connecting back to Atlanta. All right. And so that will connect me there. Then I look at the Atlanta line. From Atlanta, the cheapest edge is to Columbus, but I can't go there. I've already visited that. So the next cheapest would be, if you look at that top line, Tulsa at 772. So I'm going to connect Atlanta to Tulsa. Now I'm looking at the bottom line. I've already been to Atlanta and Columbus, but the cheapest really is to connect to Kansas City. From Tulsa to Kansas City. So I'm going to go across there. All right. Now that I'm at Kansas City, I am on the third line. Again, I can't go to Atlanta, Columbus, or Tulsa. So that leaves me with the cheapest being Minneapolis at 447. So connecting there. And then I have no choice but to go from Minneapolis to the last city of Pierre. So I have to go choose that, which would be, let's see, 394 right there. Now that I've traveled to all 6 cities, remember it is a circuit, so I will go back home. I'm going to look at the Pierre line. I have to go back to my beginning city of Columbus, 1071. So my circuit is closed and looks like that. Now, I'm going to ask you to participate by trying some of the other cities in a moment, but I want to pause and take a look at the 2 circuits that I've drawn. Now, I zoomed out a little bit here so you can see both. Now, if you look at the pink outlining on the 2 graphs, you'll notice they do not look the same. So it's highly likely that their weights are different, and one is probably better than the other. So let's see what the ultimate weight is for this particular graph. I am getting a total weight of 3,465 miles. So you can see already that between the 2 methods, that if I start at Columbus rather than Atlanta, I'm saving over 400 miles. So to finish this, what you would do is try starting at Kansas City, then try starting at Minneapolis, then try starting at Pierre, and lastly, try starting at Tulsa. I'm going to be asking you a few questions about those, and then you would choose the best of those 6 and see what that yields. Okay, in our last technique that we're going to compare, we're going to look at cheapest edge, cheapest edges. In this method, we don't worry about a starting city. We really just are grabbing the cheapest edge. We want to focus on this triangular part. Now, the very smallest of these numbers is the 248. So I need to first put my cities around here. With this method, it's very important that you have the graph. Otherwise, it becomes very difficult to see when you break one of the 2 rules. And remember, the 2 rules are don't close a circuit until you've traveled everywhere. And the other rule is do not create a vertex with degree 3. You need to leave and come to each vertex. So that's a degree of 2 on every one. So my first connection is Kansas City to Tulsa. So I draw that. My next cheapest, looking at all the numbers, would be 394. That's Minneapolis to Pierre. So I draw that in. The next smallest edge out of all those is 447. That's Kansas City to Minneapolis. There we go. Now I'm going to have to start being pretty careful. I can't, for example, draw Tulsa to Pierre. That would close the circuit without visiting everywhere. And I also can't create vertex of degree 3. So Kansas City and Minneapolis, I can't connect to those anymore because they're already degree 2. So looking at my next cheapest would be 533. That's Atlanta to Columbus. And we're good there because that's a new connection I haven't made yet. Atlanta to Columbus. Okay, the next cheapest one would be 592. That's Kansas City to Pierre. I can't do that because it would create, I'm going to draw it in and then erase it. It would create this new line here. Notice it would give Kansas City degree 3, which breaks one of our rules. So that just means we cannot use Kansas City to Pierre next. So I will just cross that one out rather than use it. All right. The next cheapest one is, let's see, 656, which is Columbus to Kansas City. And that also cannot be done for the same reason. If you go Columbus to Kansas City, notice once again it creates degree 3 at Kansas City. So I also will cross Columbus to Kansas City out. Not going to use that. Now, so we're just going in order again with the cheapest edge. Minneapolis to Tulsa. Minneapolis to Tulsa. Can't do that because if you did that, right, this would be that right there. You would create degree 3 at Minneapolis. So we have to disregard that. So I'm going to cross that one out. You see, we're losing a whole bunch of these cheapest edges. Our very next cheapest edge is Columbus to Minneapolis. And that also would create degree 3. All right. Then we have 760 Tulsa to, Tulsa to Pierre. And that one we can't do. Let me draw it in for a different reason. So I'm looking at this 760 down here. But the reason we can't do that, if we connect Tulsa to Pierre, notice that we have a closed circuit in the bottom of this graph, but it does not include all of the vertices. So we can't do that either. So we're really having a dilemma of finding this next edge. All right. So our next cheapest one is 798 Atlanta to Kansas City. And that looks to be okay. Atlanta to Kansas City is okay. If we connect those, actually it's not. Here's why. Kansas City once again has degree 3. We can't do that either. Okay, wow, we're really running out of options here. We've used all the good ones, seems already. How about, and I'm just noticing, by the way, and you may have noticed already, that I skipped the 772. I kind of went out of order. Maybe I should have gone and checked that one first. So Atlanta to Tulsa would be okay. Good. 772 is okay. Here's why. If I connect those, I have all the vertices connected now. So this is a good place where I can say I don't have to look for them anymore. So actually I didn't even need to consider Atlanta to Kansas City in the first place. Now that I have all of the cities connected, I really have no choice but to close up this circuit. I have to connect Columbus with Pierre. So I'm stuck with that, Columbus to Pierre. And that makes me choose this one with 1071. Okay, now that we have a complete circuit, let's find the weight. Okay, so I have a weight of 3,465. Okay, so how did that do? How did that compare? Well, what you see is that it's exactly the same, not only the same number as what I got when I started at Columbus, it's actually also the identical graph. All right, so you can see that when we use a different algorithm, we get a different result, and it's not always necessarily the optimal result. And that's why this problem, the TSP problem, continues to just entertain mathematicians. It's very interesting because the lack of a very good, efficient, optimal solution algorithm. I hope you've enjoyed this comparison video.